Hello everyone. In this video we are going to talk about different categories, different types of matrices, and I don't mean all of them, just specific categories like orthogonal, orthonormal, positive and negative definite, and positive and negative semi-definite matrices. So orthogonal matrix is a matrix that has columns perpendicular to each other, all of the columns. So each column is perpendicular to any other column. For example, if you have a matrix A, and this A is like, for example, 2 and 1 and negative 1 and 2, clearly the dot product of the first column and the second column is 0, which means they are perpendicular to each other. Okay, so this A is orthogonal. Now, if it happens that the columns also have unit magnitudes or they are unit vectors, we call it orthonormal. So all I need in this case is to divide basically each column in A by its magnitude. So the magnitude on each column here is square root 5. So if I divide each column by square root 5, now, not only the two columns are perpendicular to each other, they are also unit vectors, or they are normalized, so we call it orthonormal. Okay, so B is orthonormal. And if a matrix is orthonormal, we can show that the transpose of the matrix is equal to its inverse, and the determinant of that is either positive 1 or negative 1. Positive 1 for a right-handed system and negative 1 for a left-handed system. So for example here, if I go ahead and say, so if I define A here or B here, let's say B was 2 and negative 1 and then 1 and 2, the whole thing divided by square root 5, right? So that's my B matrix. Now if I say what is the determinant of B, you see it's 1. And if I say B transpose, this is this matrix. If I say inverse of B, it is the same result, right? You clearly see they are the same thing. Okay, and these orthonormal matrices are very important in many applications, including robotics and dynamics in 3D. And one of the specific types of these orthonormal matrices, which we'll discuss in one of our future videos, is a rotation matrix. Okay, so these are two categories that I wanted to tell you, and then we talk about another category of matrices, which we call positive and negative definite, and then positive and negative semi-definite, and they are used a lot in controls, especially nonlinear controls when we use the Lyapunov functions, and also in some linear systems too. So a matrix is called positive definite, and it's also shown by m bigger than 0 when if I have a vector x which is not equal to 0, so my vector x is not a 0 vector. If I multiply the transpose of x by m by x, the result is a scalar, and that scalar is positive always, for any values that I choose for entries of x, as long as they are not all 0, regardless of what I choose for x, as long as they are real numbers, the result of this x transpose mx is a scalar, is positive, and then we call the matrix positive definite. And if in all cases it is negative, we call it negative definite, and we show it with m less than 0. So what does that mean exactly? Well, first of all, when the x transpose mx is a scalar, it means that matrix M has to be a square matrix. So this matrix M has to be an n by n matrix. Otherwise, this x transpose mx is not going to be a scalar term. So what you have here is your x vector is really an n by 1. So your x transpose is going to be 1 by n. Your m is n by n. And your x is n by 1. So the result of the whole thing is going to be a 1 by 1, a scalar. Okay, so first of all, your matrix has to be square matrix. Second of all, when we say we show M as positive, it has nothing to do with every entry in the matrix has to be positive or every entry in matrix has to be negative. No, it's just a symbol. So we say M is positive, that means the matrix is positive definite. Now, what does it mean? As I said, it means this X transpose MX for any arbitrary X that is non-zero has to be positive. Now, let's look at it with an example. So let's say my M matrix is, for example, 1 and 2, negative 2 and 1, right? Something similar to that A matrix we already had. This is a 2 by 2. I choose my vector X to be arbitrary vector, and I choose the two components of it to be x1 and x2. This whole vector X should not be equal to a 0 vector 2 by 1. So it means both x1 and x2 at the same time cannot be 0. At most, one of them can be 0. So if I do so, then what's going to be X transpose M times X? Well, it is going to be x1, x2 as a row vector times M, which is 1, 2, negative 2, and 1, and then times X. So if I continue and calculate the product of the second and the third term, which is M and X, the result of that is going to be 1x1 plus 2x2, and then negative 2x1 plus x2. And if I multiply that, the result is going to be a scalar, so it's going to be x1 times the whole thing, which is going to be x1 squared plus 2x1 x2, and then x2 times the second term, which is going to be negative 2x1 x2, and then plus x2 squared. These two terms would go away, eliminate each other, and the result is going to be x1 squared plus x2 squared, which is always positive as long as both of the x terms, x1 and x2, are not 0. So clearly, you see, this matrix has to be what? Positive definite, right? This matrix is positive definite as long as the vector x is not equal to a 0 vector. Now, let's go back and look at a couple of things before we finalize our conclusion about this M matrix, which is apparently positive definite based on what we define. So, if I go back, let's look at a couple of things because they can quite be tricky. So, we said the matrix is positive semi-definite if X transpose MX is bigger than or equal 0 when vector X is what? Arbitrary. So here there is no limitation on X. X could be completely what? Arbitrary. So it could even be completely equal to the 0 vector. So in this case here, if both x1 and x2 0 or vector x is 0, clearly this result is going to be what? Positive or bigger than 0 or equal to 0. So can I call this matrix M also positive definite, positive semi-definite? Yes, sure. If you look at the definition, any matrix that is positive definite by default is also what? Positive semi-definite. Okay, so if it is positive, if M is positive definite, then we can conclude that M is also what? Positive semi-definite. Okay? Can I go backwards? So if is positive semi-definite, can I also say it is positive definite? The answer is no. Okay, because positive semi-definite is when the result of this x transpose mx, which by the way, there is a name to this guy, is called quadratic form associated with m. Just you might call it the quadratic form of m. So this quadratic form of m for a positive definite, it's always positive if the vector x is not equal to 0. If x is 0, of course the result is going to be what? 0, so it means positive definite is definitely positive semi-definite. But backwards is not always true, which means there are cases that this quadratic term is equal to 0, but those cases that this guy is equal to 0 is not when x is 0. Let's say I have a case where x transpose m times x turn out to be like x1 squared minus x2 squared. In here, this term can be equal to 0 also when what? When x1 is equal to what? To x2, and they should not be necessarily equal to 0. And not only this can be 0, if x2 is bigger than x1 in magnitude, then this term can also be negative. So something like this, not only it's not even positive semi-definite, it's completely what we call indefinite. So that's another term, let me tell you. Indefinite is a case that the matrix is not positive or negative definite or negative semi-definite or positive semi-definite. When it's none of those, so the sign of the quadratic term can be positive, can be negative, can be 0. It can take over all signs, then we call it indefinite. Okay, so in this case it is indefinite, but there are cases that x1 and x2 could be what? Could be non-zero, and the solution of x transpose mx could be what? Bigger than or equal 0 for non-zero x1 and x2. Like what? Like if I have a case, for example, let's say m is 3 by 3, so x has 3 components. I have a case like this, x1 minus x2, the whole thing squared, and then plus x3 squared. If you look at this, the result is always bigger than or equal 0 because I have the addition of 2 quadratic terms. Now, if I want this whole thing to be 0, set it equal to 0, does it need all 3 components to be 0? No. All I need in this case is x3 to be 0 and x1 to be what? Equal to x2, and they could be even a non-zero number. So if I want in this case that my x transpose m times x be 0, it means not all 3 has to be 0. That means your matrix is what? Positive semi-definite. Okay, so you see the difference between positive semi-definite, positive definite, and what? And indefinite, right? Good. Now, there is another thing that we have to talk about here, and that is, well, how do we determine this positive definiteness or indefinite or whatever? Well, the method I showed you is to form this quadratic term and then basically calculate the sign of it for different values of component of x, different entries of x. But it's not always a trivial job, especially as the dimension of m gets bigger and bigger. The term, the scalar term, is going to be larger and larger, and it needs a lot of algebraic manipulations to show whether it takes only positive numbers, negative numbers, and so on. So that's not always the most convenient method to do it, okay? Let's say, for example, I have this matrix and I give this matrix to you and say, okay, what is this matrix? Is that positive definite, negative definite, or what? So if I type this matrix in, m is 2, negative 1, 0, and so on, let me show you. See if I have it somewhere. Here. Right? Well, how can I first of all form that quadratic term? So what you can do is use MATLAB Symbolic here to help you. and you define the three symbolic variables x1, x2, and x3, and then you define vector x to be the combination of these x1, 2, 3 in a column vector format. And now you say, what is the transpose of x? When x is symbolic, do not use the single quotation for transposing. Use the command transpose. Okay, so what is the transpose of x times a times x, right? And it gives you a scalar thing. Now, this scalar thing, is that always positive? Is that always negative? Is that bigger than or equal 0 or what? You see, it doesn't look too nice and friendly like the previous cases. So one of the next things you can do, if such a thing is given, I recommend you use the command simplify in MATLAB, simplify of answer, and that tries to make it a little bit nicer for you. So what it gives you is this guy here, right? 2x1 squared minus 2x1 x2 plus 2x2 squared minus 2x2 x3 plus 2x3 squared. Still not trivial, right? But if I put it down here, right? So for that matrix, x transpose m times x was this, right? This is what you had for that matrix, correct? Okay, what is it now? Well, what I can do here is I can factor out, as I said, it needs some good algebra, but what you can do, you can take 1x1 squared and 1x2 squared and combine it with this term and make it x1 minus x2, the whole thing squared. Then you can take the other x2 squared here and 1x3 squared and this term negative 2x2 x3 and make it x2 minus x3 squared. And then there is 1x1 squared left and there is 1x3 squared left, so you can write it like this. Now, what kind of matrix is it? Well, if I want it to be equal to 0, well, first of all, you clearly see it's summation of several quadratic terms, so it has to be positive or 0. So is that positive semi-definite or positive definite? Well, if I want it to be 0, what condition do I need? If it's 0, it means each and every one of the terms has to be 0. So it means x1 has to be 0, it means x3 has to be 0, and it means x1 should be equal to x2, and then x2 be equal to x3. Correct? Each and every one of the quadratics has to be 0. And clearly, since x1 and x2 are 0, x1 and 3 are 0, that also means x2 has to be 0. So you see, the only solution is the whole vector x has to be vector 0. That means this matrix is what? Positive definite, not semi-definite. Okay, so fine, you can use it, but again, if the dimension of this goes up and this term is more complicated, even the command simplify and you trying all together might not be always trivial. So are there other ways for me to determine this positive, negative definiteness of or indefiniteness of a matrix? Yes. One of it is this. It says if a matrix is positive definite, all of its eigenvalues are also positive. If a matrix is negative definite, then all of its eigenvalues are what? Negative. So if it is positive definite, then all eigenvalues have to be positive. Now, let's go back to this first matrix that we looked at, this 1, 2, negative 2, and 1, and see whether that's the case. And we can also look at this matrix, this guy here. Let's look at the eigenvalues of these two matrices and see what we can get. So first we look at this 3 by 3 matrix. Let's look at the eigenvalues of this matrix we called A. So we say Q and D is equal to Eig of A. And you clearly look at the 3 eigenvalues. You see all 3 eigenvalues are what? Positive. So you see it is working, right? Apparently it is working. One other thing, as I mentioned initially, is when you say it is positive definite and you show it with m bigger than 0, does it mean each and every one of the entries in M are positive? Absolutely not. It has nothing to do with that. If you look, several entries in this matrix are negative. It has nothing to do with calling M the whole matrix to be positive definite or positive semi-definite or anything. Okay, so the sign of the entries has nothing to do with this positive definiteness or negative definiteness. But eigenvalues do. The sign of eigenvalues, as you just saw it, does have something to do with it. You clearly see here all three eigenvalues are positive. But what about this original one? For that one, we concluded that that matrix also should be what? Positive definite, right? Because the only situation for it to be equal to 0 was both entries to be 0. Well, let's plug it into MATLAB, see what we get. So 1, 2, negative 2, 1, right? So here I define it 1, 2, negative 2, and 1, and I apply the eigenvalue to this matrix. And boom, you get something that surprises you. The eigenvalues of this matrix are complex numbers. The eigenvalues are complex numbers. The real part of them is positive, but the complex part of them is not. So what can I say about this matrix? Can I still say it is positive definite? Well, based on the definition, yes, but there is one thing. When we talk about this vector x, what domain are we talking? That's the important thing. What domain? When we say for any x, x belongs to what? Does x belong to real numbers, or it also belongs to what? The whole set of complex numbers, which also include real numbers, right? So that makes a difference. If in this case, x is limited to what? To be a part of real numbers, of course, are squared because it's two-dimensional, then absolutely this term is always what? Positive for any real number. But the question is, what if this vector x belonged to the set of complex numbers squared? So the x1 and x2 entries could be complex numbers. Now what? Right? You see my point? So if, for example, both of them are I, the base of the complex numbers, then x square term is going to be negative, that's going to be negative, so some of it is going to be negative 2, negative 1, negative 1, negative 2. So it could be negative. So if that's the case, then this square term, there is nothing about it. And then you can say then M is what? Indefinite. If x can take over complex numbers. And the matter of fact is, if you remember, I told you that when you determine the eigenvalues of a matrix, the characteristic polynomial, which is nth order in general, it has n roots, but all of the n roots are not always real. Sometimes they are complex numbers. Okay, so it completely depends on what domain you're talking about. If my x vector that I'm dealing with in my application is only dealing with real numbers, so let's say x is the state of a system, is an input or whatever it is, most of the time it's the state of the system in a control system, and if it can only take over real numbers, which in most of the physical system it is, then really this is positive definite. But if I'm allowing it to go into the realm of what? Complex numbers, then it could be indefinite. So it completely depends what you are talking about. But know that when you do in MATLAB, MATLAB will give you eigenvalues regardless of they are real or complex. If you want to guarantee that your eigenvalues are what? Real, then your matrix has to be what? If you remember from one of our past lectures, has to be symmetric. This matrix is not symmetric, so the eigenvalues are not guaranteed to be real. if I made it symmetric like this, -2 and -2, then what would have happened? So here you would have a -2, which means here you will have a -2, and that means here you will have a -2. So it will be x1 minus, and these two will not cancel. So the result of that is gonna be x1 minus x2, the whole thing squared, then minus 2x1, x2. And this term in general can take over any sign depending on the magnitude of x1 and x2, right? For example, if they are both 2, this term is 0, but this term is gonna be what? -8. Right? If one of them is 8, one of them is 0, then this term is 0, this term is 64, so it's positive. If they are equal, again, the term can be negative, right? If they are both 0, then the term is 0. So this is indefinite in general. And I can check that if I just change the sign of one entry in M, make it symmetric. Now, if I get the eigenvalues, they are definitely real, but if you look at the sign of them, not all of them are positive, not all of them are negative. So there is no positive positive definite or negative definite condition. It is indefinite. Okay, so by looking at the signs of the eigenvalues, you can have some conclusion about the matrix, but pay attention that if those eigenvalues coming out are complex numbers, what does it mean? If they are complex number, does it mean the conclusion that we had that it is positive definite, is that gonna go away? Again, it depends. If x is real, no, it stays. If x is complex, then yes, it goes away. So it all depends. And let's say x is real. How do I know that having these eigenvalues here that are complex is not contradicting my conclusion that, well, my matrix is positive definite? Well, in this case, since your matrix only can take over, your x can only take over real numbers, what you might want to look is only the real part of the eigenvalues. If it's positive, then you can say that, yes, the conclusion I had for positive definiteness of M is correct. So I'm showing you all these tricky cases, and I'm not using all sorts of nice clean matrices. Like you could easily have a diagonal matrix, right? That you know, all I need is to just get rid of one of these numbers, right? If I just make this number as 0, what do you think would happen? The eigenvalues are going to be 1 and 1, right? Or maybe I can make this guy a 3, just to make the eigenvalues different. Now what do you think? Right? So if I do that, look. So I make this guy a 0, and then I make this guy a 3. Now if you look at the eigenvalues, you see they are 3 and 1, so this matrix has to be positive definite. Now is it? Well, this is what you do. Again, if you want to check it. So I define my x vector to be only x1 and x2, and then I calculate the quadratic term, which is transpose of x times a, in this case, times x. This is the result, x1 squared minus 2x1 x2 plus 3x2 squared. And if I say simplify the answer, it didn't really do much of simplification, but if you want to do it yourself, you basically use 1x2 from here and add it to this, so it's going to be x1 minus x2 squared, and then it's going to be plus 2x2 squared. And that is what? So if I do it for you, for this matrix here, let me add one more matrix. M is equal to 1, 3, negative 2, and 0. And you saw that x transpose M times x, if you simplify it, it would be x1 minus x2 squared plus 2x2 squared. And the only condition that can make this guy 0 is x2 is 0, and then x1 is equal to x2, which means x1 has to be also 0, means the whole vector is 0. So it's only 0 for 0x. That means this is a positive definite matrix, okay, for non-zero x's. And you saw that the eigenvalues of it were both positive and everything was clean. So yes, I could have used a simple clean matrix like this, but the reason I'm using more complicated cases with complex numbers and trying to contradict some of these conclusions is for you to look at all scenarios. And finally, there is another way to determine whether a matrix is positive definite, negative definite, or not, and that is called the Sylvester criterion. So if you have a square positive definite matrix, one way to tell it is if the leading principal minors are all having a positive determinant. What does that mean? So first of all, what's the meaning of leading minors? Principal leading minors, right? That's what it says, leading principal minors. First of all, principal minor means what? So minor, as you know, minor is really the determinant of a submatrix. So if you chop a portion of this matrix off and get a submatrix, that's called a what? That's called submatrix, and then the determinant of that is called a minor. When we talk about principal minors and leading, it means first of all, the resulting submatrix should definitely be a square matrix again. It cannot be a 2 by 3 or something, it has to be n by n. And then the way that you find them is the first one is going to be element 1, 1. Determinant of that, the next one is going to be element what? 1, 2. And the last one is going to be the whole matrix, really. So it says, in order for that, the determinant of these three matrices, the original matrix, element 1, 1, and then 1, 2, 1, 2, that all of them should be what? Positive. So this 2 is definitely positive. The determinant of the 2, negative 1, negative 1, 2, that's 4 minus 1, that's 3. So that is also positive. That's good. And then the determinant of the 3 by 3, if you use the Saros's method, is going to be 8. This is 0, that is 0, 0. So you will get a negative 2, and you'll get another negative 2. So it's going to be 4. That's also positive. So since the determinant of these three principal submatrices, or the three minors basically, are all positive, then the matrix is positive definite. Okay, that's based on the Sylvester method. Or if you used this one that we did earlier, so here this principal minor is already positive. And what's the determinant of this guy? If you calculate the determinant, is 1 plus 4, that's 5, that's also positive. So based on the Sylvester method, this matrix is also what? Positive definite. Okay, as long as, again, the vector, the realm of the vector x is only real numbers, not complex numbers. So I showed you the definition of this positive, negative, and I showed you 3 separate ways to determine them. One using the quadratic term, one using the sign of the eigenvalues, one is using the Sylvester criterion. All 3 of them can be used. So hopefully this video was useful to you. Again, where would you use this semi or positive definite and so on? Mostly it is in controls, mostly in linear, and also definitely in nonlinear controls in what we call the Lyapunov functions and so on. We definitely use this for stability of nonlinear systems. And orthonormal and orthogonal we use a lot more, especially orthonormal we use for rotation matrices in robotics and many dynamic applications in 3D. Thank you so much. We'll see you in my next video.